Welcome back to the Explainer. So today I'm going to be acting as your lead engineer, and we are preparing to boot up a complete digital twin of the Earth. But to accurately program spatial reality, well, we've got to reverse engineer the planet first. Before we start laying down code for this digital twin, I've got a fundamental question for you. Is the Earth truly round? Well, prepare to have that illusion totally shattered. Take a look at this. These are the Earth's messy, lumpy gravity anomalies, modeled as the Ch10, though, in the geosciences community, we affectionately call it the Potsdam potato. It's a great visual because it instantly shows us that mapping reality, yeah, it's going to be way more complicated than just drawing lines on a perfect globe.
So, here is our system initialization sequence. First, Earth's true shape. Then, the physical solution, followed by the mathematical solution. Step 4 is geodetic datums, and finally, navigating the curves.
All right, let's dive right into Section 1, Earth's true messy shape and the ECEF. So how on earth, pun intended, do we mathematically map a massive, irregularly shaped, rotating rock floating in the vacuum of space? Like, where do we even place the 0 point to start counting? The intuitive approach here is the geocentric coordinate system, or the Earth-centered Earth-fixed system, ECEF for short. Basically, we anchor a 3D Cartesian grid directly to the Earth's center of mass. The z-axis aligns perfectly with the Earth's spin axis, the x-axis shoots right out to intersect the prime meridian, and the y-axis forms a right angle to finish off that 3D space. The whole system just spins along with the Earth, which gives us a seemingly solid foundation. But here's the major catch when we actually try applying this to our digital twin. ECEF is absolutely fantastic if you're a satellite orbiting in space running orbital mechanics calculations, but it is frankly terrible for us humans trying to navigate down on the surface. Because the Earth is curved and uneven, you could literally have 2 points on the actual surface at the exact same physical elevation. Picture 2 boats out at sea level, but their z-values in this geocentric system, they could differ by over 17 kilometers. No way, right? It's just entirely impractical for everyday terrestrial mapping. Which brings us to our next step, Section 2, the physical solution, introducing the geoid.
We clearly need a better way to define up and down on the surface. See, because the mass inside our planet is distributed so unevenly, you've got really dense rock here, lighter material over there, gravity actually pulls in slightly different directions depending on exactly where you stand. The natural plumb line isn't perfectly straight. So the geoid is the ultimate physical reference surface that actually accounts for this. You can kind of think of it as global sea level perfectly extended underneath all the continents. And you'll also notice here the quasi-geoid, which is a closely related substitute surface based on normal heights instead of orthometric heights.
To be scientifically precise about it, the geoid is defined by gravity potential. Gravity potential describes the physical work required to lift a mass against gravity from sea level to a specific height. Out of infinite possibilities, the geoid is defined as the specific equipotential surface where that gravity potential equals exactly 62,636,853.4 meters squared per second squared. It is a true, undeniable physical representation of our planet's shape, based purely on gravity.
Okay, moving on to Section 3, the mathematical solution, featuring the flawless ellipsoid.
So the physical geoid, just like our Potsdam potato from earlier, is incredibly lumpy. It's fundamentally impossible to describe perfectly with simple mathematical equations. For our digital twin to compute distances and areas efficiently, we need a stark contrast, a pristine, mathematically smooth ellipsoid model. We create this flawless geometric shape by simply taking an ellipse and rotating it around the z-axis. It's this beautiful, clean mathematical approximation of the Earth that computers can calculate against with absolute ease. Let's anchor this theoretical model with some hard data. 21.4 kilometers. This specific number is the exact difference between the equatorial semiaxis and the polar semiaxis of the global WGS-84 ellipsoid. And by the way, that's the exact model your smartphone's GPS uses every single day. Because the Earth spins, centrifugal force actually causes it to bulge at the equator. This 21.4 kilometer difference proves mathematically why the Earth is modeled as an ellipsoid, and definitely not a perfect sphere. So with this pristine mathematical ellipsoid in place, we can finally define coordinates that make intuitive sense for those of us down on the surface. Imagine taking a really long, perfectly straight metal rod and just ramming it into the ellipsoid at an exact 90-degree right angle. The angle that rod makes with the equatorial plane, that gives us our geographical latitude.
It provides this incredibly clean mathematical surface normal, which is vastly easier to work with than that messy, curved physical plumb line we looked at earlier. All right, section 4, geodetic datums, connecting the models together.
So the crucial point is, how do we actually connect our messy physical reality, that gravity-based geoid, with our pristine, smooth mathematical models like the ellipsoid? How do we guarantee that our clean digital map actually matches the physical territory we're walking on? The answer to that profound question is the geodetic datum. By definition, a geodetic datum is the complete set of mathematical parameters that defines the shape, position, orientation, and scaling of an ellipsoid relative to the Earth's actual physical body. Think of it as the ultimate integration tool. It's the mathematical anchor that binds our holographic coordinate grid to the lumpy physical planet beneath our feet.
And this brilliantly illustrates how datum transformations work. To make a perfect mathematical ellipsoid fit a specific bumpy part of the physical Earth as closely as possible, we literally have to shift, rotate, and scale the entire digital model in 3D space to make it lock in. To actually execute this shift, cartographers use something called the Helmert Transformation Protocol. It's a precise 7-parameter programming sequence to convert spatial data between different reference systems. Step 1, 3 translations. We literally shift the digital model along the X, Y, and Z axes. Step 2, 3 rotations, where we adjust the angular orientation of those axes. And step 3, 1 scaling, which is just a microscopic size adjustment. With these 7 definitive steps, we can translate any geographic point from one mathematical reality seamlessly into another. Now, you might be wondering, why do we even need so many different datums? Well, while the WGS-84 datum works incredibly well as a global average for satellite navigation, we still rely heavily on specific local datums to optimize accuracy for regional mapping and things like property lines. For instance, North America historically used NAD27, which is based on the Clark ellipsoid, while Great Britain uses OSGB36 based on the area ellipsoid. These local datums are specifically designed to kind of hug the regional terrain much better than a one-size-fits-all global model ever could.
And that brings us to section 5, navigating the curves, traveling across these models.
Now that our digital twin is fully constructed mathematically and anchored physically, how do we actually travel efficiently across these complex, mathematically curved reference surfaces? Let's move to and see how this builds when we analyze the actual trajectories massive ships and airplanes take over our oceans and skies. On a mathematical sphere, there are 2 distinct paths you can plot between points, an orthodrome and a loxodrome.
And this right here is the ultimate navigator's dilemma. A loxodrome, also known as a rhumb line, is a curved path on the globe that maintains a constant compass bearing. It is incredibly easy to steer. The captain just locks the compass heading and goes. But it results in a longer physical distance traveled. Conversely, an orthodrome or great circle route is the absolute shortest physical distance between 2 points on a sphere. However, to actually follow it, the navigator has to constantly calculate and change their compass bearing. So it's this constant trade-off, the ease of steering a constant heading versus the fuel efficiency of taking the absolute shortest path.
Which brings us to this elegant quote from the text that beautifully summarizes everything we've unpacked today. Since the Earth's surface is regular and not strictly mathematically describable, physical or mathematical substitute surfaces are used. I mean, that really is the core thesis of this entire explainer. Every single paper map, every digital GIS application, and every GPS system you use is ultimately an elegant, highly calculated compromise between the messy, complex physics of our planet and the clean, smooth predictability of mathematics.
But before we officially log off our digital twin, I want to leave you with one final provocative thought. Our planet is entirely dynamic, right? It's not static. So when Earth's physical mass shifts, whether that's due to massively melting polar ice caps or violent tectonic plate movements, the local gravity actually changes. And if the gravity changes, the physical geoid shifts. When the physical reality shifts, what happens to all those static mathematical maps and datums we've so carefully built on top of it? It turns out, reverse engineering the planet is a fascinating process that never truly ends. Thanks for exploring this one with me.